Hey guys, we are taking a look at section 7.6 in our unit on radicals, and today we are looking at radicals, or radical and exponential equations. So far we've just been looking at radical and exponential expressions where there was no equal sign. We were just simplifying and simplifying by multiplying or simplifying by dividing and combining like terms. But today we're going to look at some equations. And add quite a few definitions and some steps, so make sure you guys are ready to take some notes. We're going to warm up our brains here and think about what we have already learned so far in this unit by simplifying these radical expressions. Now the square root of 62, wow, I cannot read that. A square root of 72 we know is not a perfect square, but we do know that there are some factors in 72 that are perfect squares. So if you start thinking about the factors of 72, we've got 9 times 8, right? We've also got 36 and 2. And I'm going to go with the square root of 36 and the square root of 2. So the product property of radicals says that we can rewrite that as the square root of 36 times the square root of 2. And then when we simplify that, we get the square root of 36 as 6. Square root of 2 can't be simplified, so it's just 6 root 2. And remember that we are sticking with our principal roots here, our positive roots. Even though negative 6 squared can equal 36, when we're taking roots, we want to stick with our positive roots. So 6 root 2. For our second one, we see a rational expression here, but we've got an irrational number in the denominator. We've got 2 plus root 3. And we learned in our previous class that the way that we fix that, we can't have that root 3 down there in the denominator, is by multiplying it by the conjugate. So 2 minus root 3. And whatever we do to the bottom, we have to do to the top. Not because of an equal sign, but because we don't want to change the value. And if we multiply something by 1, it doesn't change the value, it just changes the form. So anything over itself is a 1. So that's why we're multiplying it by both the top and the bottom. And when we multiply that, we get several steps here. It's not going to show you all the steps. At the top, we get 2 minus root 3. I'm going to actually see if I can find my mouse. Sometimes it's hard to see, and I look, oh, I think I found it. There we go. I'm going to go ahead and multiply over here. So we've got 2 minus root 3 at the top. And at the bottom, when we multiply that out, we get 2 times 2 is 4, and negative root 3 times positive root 3 is just negative 3. So we get 2 minus root 3 over 1, which we can just rewrite as 2 minus root 3, leading with our real number followed by our irrational part there, 2 minus root 3. Now 8 to the 2/3 we also know can be simplified, that we could just write that as a in rational form maybe. And what most of you would probably do, you'd write 8, and you know that that is 8 squared to the 3rd power. But sometimes that's a little bit tricky because, we do 8 squared, and if you're not super familiar with your perfect cubes, which you should be, by the way, you should know the cubed root of 64. We took a quiz on that a few weeks ago, but if for some reason you were not, I just want to point out or remind you, if you've not been told yet, that we could also do this. We could first take the cubed root of 8 and then square it. And that might be a little bit easier for you. Maybe you know the cubed root of 8 a little bit more confidently or quicker than you know the cubed root of 64. So a lot of times it's easier to take the root first and then raise it to the power. So I know that the cubed root of 8 is 2, and 2 squared is 4. So that becomes 4 when simplified. All right, so that's just a quick little review of what we've been doing so far. Let's move on to what we are doing today. We need to make sure that we are using correct terminology as we get into equations here containing radicals and just clear on our steps. So let's clarify here. Equations that contain radicals as coefficients or constants are solved by applying the previously studied methods and rules. That's our order of operations. So combining like terms, multiplying by conjugates, dividing, knowing that a negative root is, has an I that comes out, and I squared is negative 1. So those are equations containing radicals. That might look like this. X minus root 3 equals 9. Okay, that's just a random equation containing a radical. But today we are looking at a different approach because a different approach is required if the variable is in the radicand. And at that point, it's no longer an equation containing a radical, but a radical equation. So when the variable is in the radicand, we have a radical equation. Here's your formal definition. A radical equation is an equation that contains a variable in a radicand or has a variable with a rational exponent. And so we might see something like this. The square root of x plus 3 in the radicand equals 9. This is a radical equation. While our previous example was an equation containing a radical, this, because the variable is in the radicand, is a radical equation. I think I've said it 5 times, so hopefully you have that now in your vocabulary. To solve a radical equation, first we're going to follow this step. First, isolate the radical containing the variable. This shouldn't be too odd to you, because when we've solved for variables before, we've had to isolate the term containing the variable. Now, instead of isolating the term containing the variable, we're going to isolate the radical containing the variable. After we have done that, we will eliminate. So here's step 2. We eliminate the radical by raising both sides of the equation to the appropriate power. So if we're focusing our keywords here, our first keyword is isolate the radical containing the variable. Our second keyword is eliminate the radical. And you do that by raising to powers, the appropriate power, whatever the index is of the radical. If it's an index of 2, we raise to the second power. If it's an index of 4, you raise to the fourth power, whatever power you need to eliminate the radical. And then after you've eliminated the radical, you'll follow the steps of algebra to then simplify, isolate the variable term, and isolate the variable. So those last 3 steps, SII, we've been doing all year. So let's take a look at this example. This is example 2 in your book, and we're going to follow our step first of isolating the radical. So we need to isolate this root x plus 4. And we're going to do that using our reverse order of operations. So if we're using GEMDAS for order of operations here, we're going to see first if there's anything being added or subtracted that I can eliminate here. And I see a negative 2, so I'm going to eliminate that with a positive 2. So we add plus 2 to both sides. And then I'm going to go, all right, and I also see that this radical expression is being multiplied by 3. So after I add plus 2 to both sides, I'm then going to divide by 3. And that becomes root x plus 4 equals 4. So when I added 2, I got 12. When I divided by 3, I got 4. So that is step 1. All of this was step 1. Isolate that radical. Step 2 is eliminate the radical by raising to the appropriate power. And I have lost my mouse again. Where is it? I can see it writing, but I don't see it. There we go. So I've got an index of 2 here, so I need to raise to a power of 2. So I'm going to raise over here to a power of 2, and whatever I do to the left side there in an equation, whatever I do on one side, I've got to do on the other side as well. So I've raised the other side to a power of 2 as well. On the left, when I raise a square root to a power of 2, that just eliminates the root, so I've got x plus 4. And on the right side, 4 squared is 16. From here, I just follow the steps of algebra that we have been following since all of Algebra 2, Algebra 1, and even pre-algebra. We then simplify, isolate, and isolate. I need to isolate the variable here by subtracting 4. And when I do that to both sides, I get x equals 12. We then do want to plug it in and check, and we'll talk about why we need to do that in just a second. But we're going to plug that 12 back in. So we get 3 times the square root of 12 plus 4 minus 2. That becomes 3 times the square root of 16. Again, we're talking principal roots here, so the square root of 16 is 4 minus 2, and 3 times 4 is 12, minus 2 is 10, and just like we said at the beginning that this whole thing should equal 10, it in fact does equal 10, so that solution does work. Squaring both sides of an equation can introduce something called extraneous solutions. Just think of the root here of extraneous being extra. It can create a false solution, an extra solution, that doesn't work when you plug it back in. And so we always do need to check our work to make sure that we don't have any extraneous solutions. So let's take a look at an example of an extraneous solution here. All right, so we've got x to the 1/4 plus 5 equals 3. Now, we've got our variable being raised to an exponent. This is just like if I were taking the 4th root of x. It's just written in exponential form instead of radical form here. So we're going to follow the steps the same way. First, we're going to isolate that exponential expression. And we're going to do that. We've got a plus 5 here, so we need to subtract 5 from both sides. And we get x to the 1/4 equals -2. Our second step is to eliminate the radical, or in this case, eliminate the rational exponent by raising it to an appropriate power. I need to turn this into x to the 1st power instead of x to the 1/4 power. And I know to turn a 1/4 into 1, I need to multiply it by 4. So I'm going to raise both sides to the 4th power. 1/4 times 4 is 1, so that will give me x to the 1st power. And then over here, I've got -2 to the 4th power. -2 to the 4th power is a positive 16. All right, now, if I'm thinking logically for just a second here, if I were to write this as an exponent, I would have x, and according to that, x is -2. But we already know that that can't be -2, because if I did the 4th root of -2, that negative under the root sign now tells me I'm dealing with an imaginary number. So logically, I know that this number, raised to an even power, cannot be a negative number. But we're going to verify that. We're going to prove it by plugging it in here. So we're going to check x equals 16. When we plug in 16 to the 1/4 power plus 5, what I get is 2. The 1/4 root of 16 is 2. The 4th root of 16 is 2. And 2 plus 5 equals not 3. It equals 7. But according to our original problem, x to the 1/4 power plus 5 equals 3. So that did not work. That 16 was an extraneous solution. Didn't work. It's the only solution we got, so therefore there is no solution. There is nothing that raised to the 4th power plus 5. Not raised to the 4th power, sorry, raised to the 1/4 power plus 5 equals 3. No solution on that one. So you see why we had to plug that in to check for extraneous solutions. Although this being raised to an even power, or an even root, if you will, having an even root taken, we should have known that wasn't going to be negative. All right, let's take a look at some other examples. Now let's clarify that there is a distinction between an equation containing radicals and a radical equation. Hopefully you've heard me say that. I don't even know how many times I've said that in this video. There is a difference. So make sure you know radical equation is when the variable is in the radical. There's also a distinction between an equation containing exponential expressions and an exponential equation. An exponential equation is an equation in which a variable occurs in an exponent. All right, so before x to the 1/4, for example, was an expression containing an exponent. But 2 to the x power is an exponential equation. This is where the variable occurs in the exponent right here. All right, exponential equation. So we're also going to take a look at how to solve exponential equations, like 2 to the x equals 32, I think is our first example. But let's take a look at this property of equality for exponents. Okay? In technical terms, for all positive b's not equal to 1, because 1 raised to any power is still 1, if b to the x power equals b to the y power, then x equals y. So if your bases are the same and they're equal to one another, then your exponents also must be the same. So when we're solving exponential equations, we want our bases to be the same so that we can use this property of equality. So take a look at 4 to the x power equals 32. Step 1, we want to write that so that they have the same base. So we're going to write 4 as 2 squared to the x power and 32 as 2 to the 5th power. We're going to simplify that as 2 to the 2x equals 2 to the 5th. Once our bases are the same, we can say that our exponents therefore are the same. 2x equals 5. All right, I'm going to run out of time, so I'll quickly make a part 2. Got the last few minutes in that second